Alright, let's dive into something that's been making waves in the quantum computing world: quantum sources' new blueprint for fault-tolerant quantum computing. Now, I'll be honest, when I first read about this, my initial reaction was, okay, another quantum computing breakthrough claim. But as I dug deeper, I realized there's something genuinely unique here. It's not just about incremental improvements, it's a fundamentally different approach. So, let's break it down. First off, the hook. What if we could combine the best of both worlds? The long-range connectivity of photonic qubits and the near-deterministic entanglement of atomic qubits. That's exactly what Quantum Source is proposing. And personally, I think this hybrid approach is where the future of quantum computing might be headed. It's not just about photons or atoms, it's about how they work together. Now, let's set the stage. Quantum computing today is a bit like a race with no clear winner. Superconducting qubits are fast, but lack connectivity. Trapped ions have great fidelity, but struggle with scalability. Photonic qubits. They are fantastic for connectivity, but stumble when it comes to creating entanglement. Each platform has its strengths, but none ticks all the boxes. And that's where this blueprint comes in. It's trying to solve the connectivity and entanglement problem in one go. Here's the core idea. Quantum Source introduces a reusable unit cell, a rubidium-87 atom trapped in a high-finesse cavity. What makes this really interesting is how it replaces probabilistic photon-photon interactions with near-deterministic photon-atom interactions. In my opinion, this is the game changer. Photons are great for transporting information, but they are terrible at interacting with each other. By bringing atoms into the mix, you're essentially giving photons a partner that can handle the heavy lifting of entanglement. One thing that immediately stands out is the elegance of this design. The unit cell isn't just a single-purpose component, it's a Swiss Army knife. It prepares and measures atomic qubits, generates single photons on demand, and performs entangling gates. What many people don't realize is how rare it is to see such multifunctionality in quantum hardware. This isn't just about reducing complexity, it's about making the system more efficient and scalable. Now, let's talk about why this matters. Fault-tolerant quantum computing requires two things: scale and connectivity. Scale means having enough qubits, and connectivity means being able to entangle them efficiently. Quantum Source's blueprint addresses both. By reusing atoms and leveraging photons for long-range connections, they are cutting down on hardware overhead while maintaining high connectivity. If you take a step back and think about it, this could be a blueprint for how we build quantum computers in the future, not just a theoretical exercise. But here's the catch: this is still a blueprint, not a finished machine. Experimental validation is ongoing, and there are engineering challenges ahead. Reliable atom trapping, high-finesse cavities, fast optical routing, these aren't small feats. Yet, what this really suggests is that the path forward is clearer than ever. It's not just about solving one problem, it's about integrating solutions into a cohesive architecture. A detail I find fascinating is how this approach aligns with the measurement-based model of quantum computation. Instead of executing gates sequentially, the system builds a large entangled state and computes by measuring it. This isn't just a technical detail, it's a paradigm shift. It's like moving from assembly line manufacturing to 3D printing. The atoms act as reusable stitching points, tying together photonic qubits into a computational fabric. This raises a deeper question. Could this be the architecture that finally bridges the gap between theoretical quantum computing and practical applications? Personally, I'm excited but cautious. The numbers look promising, a photon loss threshold of 2.6% per gate, for instance. But there's still a lot of ground to cover. Non-Clifford gates, for example, are essential for universal computation, and Quantum Source hasn't fully optimized those yet. Still, This blueprint feels like a significant step forward, not just for quantum source, but for the entire field. In my opinion, the real takeaway here isn't just the technical details, it's the philosophy behind the design. Instead of forcing quantum systems to do what they are not naturally good at, this blueprint leveraged their strengths. Photons handle connectivity, atoms handle entanglement, and together they create something greater than the sum of their parts. If you ask me, that's the kind of thinking we need more of in quantum computing. So, where does this leave us? Quantum Source's blueprint isn't a finished quantum computer, but it's a compelling roadmap. It's a reminder that sometimes, the best solutions come from combining existing ideas in new ways. Whether this becomes the foundation of future quantum computers remains to be seen, but one thing's for sure, it's a conversation starter. And in a field as fragmented as quantum computing, uniting physics and engineering might just be the breakthrough we've been waiting for.